another 90 minutes. So if we had full kind of design of this program for the 2 days without external constraints, I'd probably give this lecture tomorrow, because hearing 3 hours of me drone on, I even get bored of hearing myself for so long. But we couldn't quite do that for travel and some other logistic considerations, so we jammed the 2 lectures that I'm doing into this one day. And then layered on top of that, the writing one was relatively easy to hear, I think. This is technically more challenging material, so we just ought to acknowledge that at the beginning. And if there's a few details that are a little hard to absorb, I'm trying my best to reach an audience with diverse backgrounds and interests, and I hope you'll accept my apology at the front if I don't hit the mark exactly. So this is about indoor particles, one of the big categories of indoor air contaminants. And here are the themes that I want to address. You'll notice the familiar green and yellow stripe and the blue headlines. It was interesting to see Andrea adopting that without amendment, but okay. Even the font style was the same. So the themes. An assertion: indoor particulate matter matters, is important, and size is one of the attributes of particles that really drives the system. So size matters a lot. We'll talk about the metrics that are used, as has taken place in the earlier subject tutorials, both in ventilation and exposure. What it is that we're measuring and how we measure it is really central to our ability to do science. We'll talk some about the underlying physics of airborne particles, and I want to introduce now, and we will elaborate quite a bit on this, the notion of a universal U, which means in many situations when we're looking at particular processes that affect particle behavior, that behavioral outcome as a function of diameter is U-shaped. Stronger in the ultrafine, stronger in the coarse particles, weaker in what's called the accumulation mode, the middle-sized particles. Material balance models, we can't escape them. They're everywhere, so we'll take a look at the material balance model with some applications. I don't think there's a meaningful overlap here, maybe a little bit with infiltration factor with what Andrea presented. And then just an introduction to some research frontiers. Michael Waring mentioned at the introduction that you will receive an email this evening, I guess, that has references for this talk. There's about 50 articles, that some of which are specifically cited and others that are sort of on a suggested must-read list if you want some perspective and background. So there are a few slides where I have a lot of references that aren't detailed. You'll get those detailed references later. I overuse this cartoon and this quote. They're my guideposts for life. Everything should be as simple as possible, but not simpler, which is brilliantly twisted. And the cartoon illustrates that brilliantly as well. I would say that the Einstein on the right is simpler. It's not as simple as possible. Maybe the Einstein in the middle is about as simple as possible. That is, you can still recognize that it's Einstein. Okay, so we'll see a little bit about what that means as we go along. But the idea is to try to not get lost in the details when the details are not important, but to be cognizant that there are details, and sometimes those details are important. So why does PM matter? Why does indoor PM matter? There's a ongoing study, it's been going on for a quarter century now, called the Global Burden of Disease Study. And the researchers involved in this study are compiling data from all manner of sources, aggregating it and analyzing it to try to quantify and place a rank order on what it is that causes ill health in the human population. They do it geographically specific, but also globally. They do it sex specific, and they look at underlying causes. In the latest report published in 2017, which was for year 2016, they listed the top, 74 risk factors, or the 74 risk factors that they had quantified. And among those were 3 that are specifically particulate matter. Their rank order is listed here. So ambient particulate matter, household air pollution, which refers specifically to the emissions from cooking with lower quality fuels like solid fuels, as pictured in the middle photo here, and then exposure to environmental or secondhand cigarette smoke. And you can see that these 3 rank in the top 30, and 2 of them rank in the top 10 among all causes of ill health. And other things that we consider as big environmental problems, like unsafe water, unsafe sanitation, no access to hand washing, are not stronger in their contributions to ill health than these particle-related issues. I assert that it is evident that 2 out of those 3 are indoor problems. Secondhand smoke is mainly an indoor issue, although smoking is not allowed in many public spaces, it still occurs in private spaces. In fact, it's the fact that it only occurs in private spaces that pushes it down to 20 to 30 in rank rather than in the top 10 to 15. Household air pollution, quite obviously an indoor problem. It's mainly, and you can see the higher rank for women and young children who are exposed because women do more cooking in these circumstances. And I will also claim, and I will justify this claim as we go along, that the ambient air pollution or ambient particulate matter problem is actually an indoor problem mainly as well. And the reasons should be relatively clear from the discussion that's preceded today. We spend most of our time indoors. Indoors provides imperfect protection from outdoor particulate matter. And so even if you don't account for indoor emission sources, most of what we inhale that's ambient PM, we inhale while we are indoors. All right, well, this is exposure, again, just to remind you that the people are indoors. Time budgets for Californians, similar for the rest of the United States, similar for actually every population that's been studied, only different in some subtleties. About 90% of our time is spent indoors, and about 2/3 of all our time is spent indoors in our own home. So buildings protect, and they protect imperfectly. This is also an exposure type of investigation. So I did work for about 5 or 6 years in Singapore, during which I spent a year out of that 5 years, about 20% of my time resident in the country. And Singapore, quite remarkably modern country with generally good environmental quality, has a seasonal problem associated with regional agricultural burning. So it's burning in nearby islands, Sumatra and elsewhere in the neighborhood, Malaysia, that are intended to clear agricultural land so that palm plantations, palm oil trees can be planted. And the burning is done in an uncontrolled manner and produces quite dramatic haze. So I was there during the worst of the recent episodes, which was in 2013, and you can see 2 photographs here, and that's about right. That tall building that you can see on the right is also the same image that's obscured by the smoke on the left. It was several hundred meters only away from the building where I was taking the photograph. So under the heading, we didn't set out, the research program that I was a part of there was designed to do research necessary to make buildings more energy efficient in tropical climates in modern economies. And my role in it was to help ensure that as we aimed to improve energy efficiency, we didn't make indoor environmental quality work worse for the occupants of those buildings. We didn't set out to study haze, but under the good heading of if you're given lemons, why not make some lemonade? This episode happened, and we had some personal monitoring equipment, and we said, let's do a personal monitoring study. So we took about 10 of these handheld, medium grade optical particle counter instruments, battery powered, and had members of our team carry those around everywhere that they went for a week. And then we measured with those instruments what effectively the people were being exposed to as they would go about their day. So this image at the bottom illustrates one day's exposure profile. It was actually mine. I stayed at a hotel that had mechanical ventilation. It's kind of similar to the one I'm staying at now. No ability to open the windows, and had a little bit of filtration. And so the particle levels were lower. I walked to the office where I worked, and you can see that exposure during my walking period. Inside the office, which is called the Create Tower, some mechanical ventilation and some filtration reduced my exposure. I went outside for a lunchtime walk, and you can see the rest of the details. You can estimate just by looking at a comparison between the trace when I'm outdoors and when I'm indoors what the protection factor is associated with being indoors in this case. And it was about 50%. That 50% represents the outcome for PM2.5 of decent quality but not good quality filtration. Good quality filtration could achieve an order of magnitude improvement. And an order of magnitude improvement is what would be necessary to take the polluted outdoor condition when the haze was high and turn it into a condition that would meet air quality standards, let's say, set by the World Health Organization, health-based. So buildings protect imperfectly. Not uncommon to get a factor of 2 improvement. There's one other quite important issue that I want to just set up as context for our discussion today, and that is the notion that what we know about health consequences of being exposed to particles is limited in strong measure by what we are able to characterize with respect to exposure. We know pitifully little about true exposure in indoor environments to particulate matter. We know pretty well what urban PM2.5 levels look like. We know pretty well what coarse particles is larger than PM2.5. I'll elaborate or explain more precisely what these measures mean momentarily. So the coarse particles are bigger, but the coarse particles measured outdoors are not a very good indicator of what we're actually being exposed to indoors, because indoor sources like resuspension matter a lot. We don't know very well the very smallest particles in urban air. We're not monitoring them routinely, and those don't penetrate and persist very well in indoor environments, and they're strong indoor sources. So we have poor knowledge about our real exposure to ultrafine particles. PM2.5, we actually have decent information because buildings only protect a little bit, and absent cigarette smoking and strong emissions from cooking, which are only episodic, the outdoor sources are a major contributor to indoor levels of PM2.5. So this is a little bit like lamppost science when we claim that PM2.5 is the most harmful aspect, a claim sometimes made, most harmful attribute of particulate matter. It's like this joke here, a man searching diligently under the lamppost at night, the passerby, he tells, "I've lost my keys," or he answers, "I've lost my keys." "Did you lose them under the lamppost?" "No." "Well, why are you looking here?" "Because that's the only place I can see." We have a big, fundamental, important problem to address, which is what are we really exposed to with respect to ultrafine particles? Do they really pose the kinds of adverse health effects that we think may prevail based on laboratory investigations or investigations with laboratory animals? And a similar thing with coarse particulate matter. Exposure with respect to particulate matter is a huge unsolved problem at this point. All right, so here are the basic definitions. We are interested in the condensed phase. It could be liquid, it could be gas, liquid, it could be solid, it could be a mixture thereof. The individual elements finely dispersed that remain airborne for significant amounts of time. The smallest entity in this category is something that is at the boundary of what you would call a molecular cluster, but it's bigger than that, and that's a fuzzy boundary. So the smallest thing might be a nanometer in diameter, or maybe you say 3 nanometers as a starting point. I'm not going to argue about what's the beginning edge there. At the upper end, we're only interested in things that are respirable, that can get into our respiratory tract, and that remain airborne for some significant period of time. So if you get beyond 10 micrometers, it starts to get a lot less interesting very fast because the particles don't make it deep into our lung if inhaled, and they settle out rapidly out of the atmosphere. Within that range, if you look at the whole range, we're talking about 5 orders of magnitude in diameter. Mass scales as the cube of diameter, as volume does. So we're talking about 15 orders of magnitude in mass. And I could spend more time than we have, and I won't, trying to impress upon you how vast 15 orders of magnitude is. Let me just tell you, it's bigger than you can imagine. And you can think about it as an exercise later if you don't believe me. Rather than, we often, and when we're able to, talk about the size in detail, but we often cluster particles into different size categories just to make our life easier, keeping it as simple as possible, but not simpler. So then we might talk about the ultrafine particles, those that are smaller than a 1/10 micron in diameter, the coarse particles being larger than 2.5 microns in diameter, or maybe 2, and then the accumulation mode in the middle. And why it's called the accumulation mode will become clear, but it's tied with that universal U idea. So, I've struggled to try to make an impression upon people why the size variability matters so much. And a graphic that I came up with recently, which was inspired by Lindsay Marr at Virginia Tech, she came up with the labels, but I came up with the figures, is to say, if particulate matter was an animal category, it wouldn't just be a species, it would be a whole category like mammals. And if it's a whole category like mammals, we can map the size range, this is done on a mass basis, between the different sizes of the particles and then the different sizes of the mammals. And maybe you can get a sense from this of just how vast the variability is that we're talking about. So the smallest mammal we could find was the shrew, and if you scale the shrew, which weighs 2 grams, to a 20 nanometer particle, and say that that's my analogy, so 2 grams is equivalent to the mass of a 20 nanometer particle, then a pretty big coarse particle, a 9 micrometer diameter particle, would correspond to 180 tons, which is the size of the biggest whale, the blue whale. And if you like the fine particles, you're a cat and dog lover. We measure then many different aspects of particles and talk about them. And with respect to indoor particles, here's a little terminology. Some of it's general beyond indoor particles, and then the lower parts specific to the stuff that we'll talk about with indoor particles. So PM 2.5 is the most important regulated particulate matter pollutant today, and it's the mass of condensed phase materials per volume of air, where the diameter, the effective diameter of each particle is 2.5 micrometers or smaller per volume of air. So it's measured in micrograms per cubic meter. The measurement technique, the standard measurement technique, is you draw air through some sort of device that throws away the larger particles, like a cyclone, and then pass that residue through a filter that captures everything. You measure the mass gain on the filter and normalize it by the total volume of air sampled, and that gives you a mass concentration. That's PM 2.5. If your cut point is at 10 micrometers, not at 2.5 micrometers, that's PM 10. And so PM 2.5 is a subset of PM 10. UFP, or ultrafine particles, is a measure of the particles that are in the accumulation mode, 100 nanometers or smaller, and that size mode, each individual particle contributes so little to the mass that the UFP basically doesn't impact, even though it's part of PM 2.5, there's no real relationship between the UFP scale and the PM 2.5 level. And so for ultrafine particles, our aggregate measure that's most common is to measure number concentration of particles without size discrimination. And I'll show you some instruments that are used for making these types of measurements. So when we come indoors, then we could talk about the indoor-outdoor ratio. That's just what it sounds like, and it would take into account the effects of indoor sources as well as the penetration and persistence of outdoor particles. Or we could talk about the infiltration factor, which is an idea that Andrea introduced. So that's the indoor concentration normalized by the outdoor concentration when you remove the influence of indoor sources. And we could talk about penetration factor, which is if for the air that leaks through the envelope, what fraction of the particles in that leaking air, the infiltrating air, as Andy told us about, makes it into the indoor environment, what fraction is lost. We also actively remove particles with filters. So we have the idea of filter efficiency, which is a fractional removal of the particles of a given size as air passes through a filter medium. And then we can speak about the effectiveness of an air cleaner, and we'll get to this at the end of the lecture, where the effectiveness describes not what fraction gets removed as the air passes through the filter, but what are the consequences of deploying an air cleaner in reducing the concentrations within the interior space. That's more directly effective for controlling exposure. A little bit now about measurement methods. So this is a really skim the surface of what could be a whole lecture. No instrument's capable of measuring everything. Some key issues that we have to consider are the size range that the instrument is sensitive to and the resolution. Does the instrument provide detail about the particle size, or just does it provide an aggregate measure? Are we making a time-resolved measurement? We get some instruments that can do instantaneous readout and give us a continuous record of how concentrations vary with time, or do we do time-integrated sampling we've talked about a little bit for gases during the conversation today with either a passive sampler or an active sorbent-based sampler. Do we measure composition, or are we composition insensitive or composition blind? What are the cost, performance, portability, stability of the instruments? Some of the major alternatives, so light scattering is a principle. I mean, it's why the haze was so visible. Particles scatter light brilliantly, and that becomes then a powerful lever with which to monitor particles in air, and a lot of instruments are based on light scattering. We can use electrical mobility, that is how fast an electrically charged particle moves in a controlled flow with an electric field, to sort and size particles. There's an instrument that's quite widely used, very powerful in concept, called a condensation particle counter, which uses light scattering to detect, but it doesn't do size-based measurement. It basically causes all the particles to become big enough so that they scatter light efficiently. And that's a quite good device for measuring ultrafine particle concentrations. And then filter-based sampling is the standard method for time-integrated measurements, like standard techniques, and it's used for a lot of chemical composition information. I'm not going to say anything more about it, but I want to show you a little bit about the three other ideas. So this is a condensation particle counter that is kind of a new invention in this space because it's using water as the working fluid, whereas the older ones used butanol and alcohol. It's kind of nasty smell and not very friendly to be using indoors. So in this instrument, the air is drawn in from wherever you're sampling it, and it passes through what's called a conditioner tube, where the walls of the tube are wetted and the tube is heated. And so it's wetted with water, and it creates elevated water vapor concentration within the tube. And then the air passes into what's called the growth tube section, and in the growth tube section the walls are cooled. So now as the coolth of the walls diffuses into the core of the air, the water vapor concentration begins to exceed the saturation amount, and the water vapor is not happy being in the gas phase, to put an anthropomorphic spin on this. So the water wants to condense, and particles are a great substrate for condensation as long as they're bigger than some minimum size, which is down in the nanometer scale. So every particle that is larger than a few nanometers will experience a surge of condensation of water molecules, causing it to grow up to 3 or 5 micrometers, depending upon the exact design details and the concentration of the particles. So then those larger particles now pass into a sensing volume, and by using a solid-state laser and optical detection, we can see from light scattering when a particle passes through that volume. Every particle gets counted if it's large enough to serve as a condensation nucleus. And this is insensitive to the size of the particles, because it turns out from the underlying physics that independent of how large the initial particle was, it will grow to almost the same size under the same conditions. So good real-time measurement, good ultrafine particle detection, really robust and useful in field settings, not so easy to carry around. I don't know of a personal exposure study with a CPC, but one could in principle do that. Electric mobility is kind of the poster child instrument is called an SMPS, it does say scanning mobility particle spectrometer. And the basic notion here is that you're interested to measure small particles, is mainly for ultrafine or the lower end of the accumulation mode, and measuring them from a polydisperse atmosphere, but capturing the size in addition to capturing the total number concentration. And so the air that you're sampling is drawn into what's called a neutralizer that uses a radioactive source, maybe some other source as well, to generate a strong cloud of positive and negative ions. And that strong cloud of positive and negative ions nominally causes neutralization, but what that really means is not that all the particles are electrically neutral, but that they all have a well-described distribution of electrical charge, which is mostly zero for the smallest particles, but will have some +1 and -1 charges as well. So that known distribution of charge is then brought into an instrument, and air flows down this annulus, and there's an electric field provided in the transverse direction between the outer wall and the central core. And so only particles that have exactly the right combination of the electric force field applied to them and the drag caused by airflow resistance will make it to the outlet, and then they get sent into a condensation particle counter to get detected. So by scanning through different voltages, then this can select different particle sizes, and you can get a complete makeup within several minutes of what the fine particle size distribution is. And then the third instrument is optical particle counter. So these are really effective for particles that scatter light a lot themselves, which sets a lower size limit. The rule of thumb here is that particles scatter light really well when their diameter and the wavelength of light are comparable in dimension. The wavelength of visible light, green, is 0.5 micrometers. We can measure 0.5 micrometer particles with this kind of instrument brilliantly. We can measure down to about 0.1, but below 0.1 the particles just do not scatter enough visible light. And then at the upper end, they still scatter a lot of light, but when you get above about 10 micrometers, it's very hard to reliably deliver the particles into the sensing volume. So it's a really good instrument in the range of about 0.1 to 10 micrometers in principle, and some specific instruments are narrower than that. Part of the challenge here is that the light scattering, although it's strong, is sensitive to the chemical composition of the particle, and it may be sensitive to the shape of the particle. So laboratory calibrated instruments may not work in exactly the same way quantitatively when you take them out into the field. And if you're measuring soot particles, you'll get a different response than if you were measuring secondary organic aerosol or something of that sort. Andrea talked about, and I don't have much more to say than she did about these consumer grade devices, so-called, where the costs are in the few hundreds of dollars. I just want to highlight that there's a new research article we've just are about to publish. It's available online, entitled Responsive Consumer and Research Grade Indoor Air Quality Monitors for Residential Sources of Fine Particles. So if you're interested in the performance of these kinds of devices, you might want to take a look at that. Okay, let's shift gears a little bit and talk about the dynamics, and here I mean physical behavior of the airborne particles. This is also a slide that has a lot of parallel to what Andrea showed you. We would like to, sort of a wonderful goal to aim at, the holy grail for indoor aerosol dynamicists, is to have a mechanistic, quantitative understanding of the relationship between governing processes and particle concentrations as they vary in space and time in all indoor environments under any possible circumstances, including chemical composition and the size of the particles and their shape and their fate, and the source attribution and respiratory consequences when they're inhaled. Okay? That's an exercise for the audience. You can carry it out in the next career of yours. I set out to work on that problem, and we made, against that big goal, we made identifiable progress, but quite modest on scale. So our outcome variable, composition resolved particle size distribution for any indoor environment, with proper characterization of the spatial and temporal variability, with appropriate characterization, I said all this stuff already, of the influential parameters, the outdoor particles, the indoor emission sources, the building ventilation and indoor airflows, the filtration, the deposition, the gas to particle conversion processes. This aim, this ultimate goal, is quite far beyond our current reach, so we have to make compromises. Make the thing as simple as possible, but not simpler. We try to make those compromises in a wise way so that we, for the purposes that we are undertaking the work, we get meaningful information, even recognizing that some things we can't do as well as we would like. So I want to, with that as kind of a holy grail goal, and recognizing our human frailty and shortcomings that we're not going to get there anytime soon, talk a little bit about the things that we really do know well enough to help inform how we simplify the problem in order to get useful information, even if we can't do the perfect thing. And this is a bit of aerosol physics, and again, if you've seen it before, this will be a breeze, and if you haven't, it may, there's a phrase I heard, MEGO, my eyes glaze over, M-E-G-O, and I apologize if that happens to you. It's not too many slides like this, so let's just proceed. So the one important mechanism that affects particle behavior when suspended in air is called Brownian motion, or diffusion. It's the analog of molecular diffusion. It results from the consequences of the bombardment of each particle by the gas molecules, not other particles, by the gas molecules that surround it. And those are phenomenal in number, but particles are massive compared to individual molecules, so each momentum exchange typically doesn't cause the particle to move very much. As the particle is bigger, its resistance to being influenced by this process gets rapidly weaker and weaker. So this is a process that matters for the smallest of the particles, the ultrafine particles, and especially the nanoscaled ultrafine particles. And it gets really unimportant almost by the time you're in the accumulation mode, and completely negligible in its consequence in the coarse mode. An outcome, a way to describe the process, is Fickian diffusion, which talks about the fact that if you have a non-uniform concentration in space, then things will migrate from the higher concentration towards the lower concentration. So there is a flux that scales with the rate of change of concentration in position. It's from high to low, which is why there's a minus sign in the flux expression, and the proportionality constant is called the diffusivity. It was actually Einstein who gave us the equation that we currently use, at least a part of it. It's called the Stokes-Einstein relationship, and this has a slip correction factor in it that I'll explain a bit about momentarily, allowing us to determine the diffusivity of a particle from its size. So this is the viscosity of air, the Boltzmann constant, temperature, and then this is a slip correction factor. And one really useful rule of thumb is that if you know the diffusivity, then over any time period tau that you might want to express, as long as it's above some really tiny amount, the expected travel distance that particle will be able to move by means of this mechanism. It's random. It's going to go in all kinds of different motion. But if you look at time 0 and then time 0 plus tau, how far has it traveled? The expectation is that it's going to scale with the square root of the diffusivity and with the square root of time. It relates to a physics principle called the random walk. One thing, I don't have a lot about the slip correction, but let me explain just in a moment what that means. All of the things that we're interested in looking at typically look at the relationship between an impetus causing a particle to move and the resistance to that motion caused by the drag of the particle moving through air, which has a viscosity and has mass, so it also has some resistance from that point of view as well. The theory on which Stokes' law is based, describing viscous resistance of a spherical body immersed in a fluid, assumes that the fluid is a continuum such that the properties that we describe, like viscosity, like density, apply all the way at the smallest possible scale. But when you get to the smallest possible scale, and 10 nanometers certainly qualifies, the fluid is not continuum. It's a lot of gas molecules that are bouncing around. And it actually turns out that the physics behaves differently down in that range. And so the way we address that is to continue to use Stokes' law, and then we're engineers here, we add a correction factor. And the slip correction factor is a function of how big the particle is compared to how grainy the gas is. So that's what this C sub C represents. If you look at diffusivities as a function of particle diameter, the qualitative point that I made before is reinforced here. So across the range of sizes, you can see this incredibly steep descent in this key transport parameter. And I just suggest to you now, without a lot of defense for it, that these numbers are big enough to matter in many circumstances, and these never do. They're too small. A second transport mechanism that's always at work in Earth's gravitational field, at least, is gravitational settling. So the particles experience a force because they are mass and they're in a gravitational field. They are more dense than the air that surrounds them, so that there's a net acceleration drawing them downward. That acceleration is resisted by the viscous interactions with the gas molecules, and the steady state force balance produces a settling velocity. That settling velocity turns out to scale with diameter squared with the fudge of the slip correction factor. It depends upon the density of the particle, and it's inversely proportional to viscosity. Here's an expression if you want to be able to calculate the slip correction. Only worry about the slip correction if you're dealing with particles smaller than a micrometer in ordinary atmospheric conditions. If we plot settling velocity as a function of diameter, you see the complement of mirror image of the plot that I previously showed you. Completely irrelevant for nanoparticles, but important enough to matter when the particles are in the coarse mode. Now let's say you take a small whatever, air flowing between two horizontal plates in a channel, and that air contains some particles, and you're interested in the fate of the particles as the air moves through that channel. That might be like the crack around underneath a door or around a window. The really tiny particles, as the air flows through, are going to move up and down because of Brownian motion. And particles that strike something else, this is a good rule of thumb, stick. If you ballistically blast them at something, they may not stick, but most of the time they stick. So the question really is, can a particle that's moving up and down like this collide with the wall of your crack before the air takes it through? If the particle's big, air flows through this channel, and the particles are going to settle, and they're going to land on the bottom if they're settling fast enough. The particles that are most likely to get through this crack are neither the smallest nor the biggest. They're the particles of the intermediate size, and that introduces the beginning and the origins of this idea of the universal U. There are a lot of situations in which particles are brought into close proximity to a surface, and that final movement has to be governed by some kind of mechanism. And that final movement is typically multiple mechanisms acting simultaneously. It's the sum of those mechanisms, at least in concept, that influences the outcome. So when you have particles in this middle size range that are too big to diffuse and too small to settle rapidly, they will hang around the longest in that air parcel. And here I've just shown kind of a crossover of two plots, one showing how far a particle would travel by gravitational settling in just an arbitrary 10 seconds, and then how far a particle would diffuse in 10 seconds. And this is the particle that's going to be the most persistent in air because it travels the shortest distance by the combined mechanisms on that time scale. And you notice I want to call your attention to the size that we're talking about, 0.2 to 0.3 micrometers. We'll come back to this size with some other elements. I do want to introduce one other important transport mechanism before we move on and look at some applications, and that's the idea of inertial impaction. So air flows around obstacles. This is the way fibrous filters work. A HEPA filter, for example, is a bunch of fine fibers, cylindrical, oriented crosswise to the airflow, and air flows, the particles don't get strained. Don't misunderstand this. The air flows around the fibers, and the particles that have too much inertia, they want to continue in a straight line, the drag is not strong enough to push them around the corner to follow the streamline, they collide and impact with the fiber, and they're collected. They're removed from the air as a consequence. So the critical parameter here turns out to be something called the Stokes number, which is the ratio of the stopping distance of the particle to the flow disturbance length scale. Here I have pictured, let's say, a cylinder in cross-section with uniform flow around it. The disturbance length scale is how far upstream of the obstacle you have to go to see bends in the streamline. Turns out to scale very well with the size of the disturbance. So the diameter of the fiber is a good measure of the disturbance length scale. And then here you see some particle that's just got too much inertia because it has to be accelerated to change its flow direction. That acceleration can only come from drag. If the inertia is too much for the drag that's available, the particle is going to continue in a straight line and collide with the surface. And the stopping distance, by the way, is just how far a particle injected at velocity u0 would travel before coming to rest with drag as the only force mechanism in stagnant air. So think about a respiratory tract. A respiratory tract is a branching airways. Of course, you're using it, as we all are, every few seconds, inhaling and exhaling. When you inhale the air has to go through this branching network. So we start at the head region, which does some of the work of humidifying and adjusting the temperature, but it's just purely conducting airways, relatively large diameter, maybe a little complications through the nose. Then there's a series of branching airways called the tracheobronchial tree. It's a binary bifurcation at each generation. That is, each airway branches into two airways of equal size, and then that branches into two more airways of equal size. You go through something like 13 generations in the tracheobronchial region, and you reach the alveolar region. The alveolar region is the gas exchange zone of the respiratory tract. It's the deepest part of the respiratory tract. There continue to be branches down there, but attached to each of the airways are these little alveoli in which the gas exchange happens. There's a very thin mucus layer and very little separation between the blood and the air. So oxygen moves well from the air into the blood. CO2 moves well from the blood into the air. And particles that are in this airstream have some chance of depositing. Where they deposit has consequences, and the size of the particle strongly influences the probability of depositing and the location of the deposition. So I have depicted here model predictions, which are well supported by experimental data, from a 10 nanometer up to 5 micrometer particle diameter. The red line shows the deposition as a function of particle diameter. The fraction of the particles that deposit as a function of diameter anywhere in the respiratory tract. So where it says 0.8 here, what that means is that 80% of the 10 nanometer particles that you inhale don't get exhaled. Where it says 0.2 here, then only 20% of those particles get inhaled, the rest get exhaled. There is an extraordinarily common error made by people even who should know better, and by many people who I will forgive because they don't know enough to know better, that the smaller the particle, the deeper it penetrates into the lung. That is patently wrong. The deposition pattern is U-shaped. If you look in the deepest part of the lung, this is called the alveolar or pulmonary region, you actually get this two-hump camel in terms of deposition efficiency. So the fraction of the inhaled particles that make it into the pulmonary region and deposit in the pulmonary region has a peak at about 30 nanometers, 30 or 40 nanometers, and larger and smaller particles deposit less efficiently there. Why in the larger size? Because these particles don't diffuse rapidly enough, and diffusion's controlling the deposition process. Why in the smaller size does this go down? Because the air has already traveled through your head and your tracheobronchial tree, and the removal is like pre-filters. The removal of particles in those zones has protected the pulmonary region from exposure. The same thing happens in coarse mode, that the peak of pulmonary deposition in the coarse mode might occur at about 3 micrometers. Larger particles don't get through the tracheobronchial tree or through the head to begin with, and smaller particles don't settle rapidly enough or don't have enough inertial impaction to deposit. It's U-shaped, and the minimum of the U is similar to that cartoon slide that I presented earlier. Okay, I don't have to preach. Let's talk a little more about material balance. So you've seen some introduction to this. I just want to dig a bit deeper than Andrea did. Our equations are going to have a few more terms, but not get seriously more complicated in their analysis. So here is one zone representation of an indoor environment with the volume and with the concentration. And if we're thinking about particles carefully, we might want to think about C being concentration of particles of a particular size. But we could get away with maybe talking about PM 2.5 behaving like this. We just have to be careful about first order parameterization of different processes then. The airflow into this interior space is divided into 3 parts. There's a supply part that may come through a filter. That filter could remove the particles, some of the particles with a certain efficiency. There's a natural ventilation component indicated through an opening here that's going to have no particle attenuation at all. And then there's a leakage part, the infiltration component, and some of those particles may not make it through, depending on how big and small they are and what the tortuosity of the path is. The airflow has to be balanced, so the sum of the flows in has to equal the sum of the flows out. We may have active recirculation of flow through a filter to try to control. So we have a flow rate and a removal efficiency here. We may have an indoor emission source. We may have a deposition process that we need to account for. The ones that are placed in boxes here have strong size dependence, basically everything. I should have put C as well. And then there may be strong dependence on time for many of these parameters as well, particularly the ventilation flows and the emission strengths. And we could generalize this model to multiple different interior compartments with interzonal flow to connect them one to another. This gives us a foundation conceptually to then write the material balance equation, which is the same thing that you've already said, just with with just a few more details here. So this is our accumulation of particles in the interior space, the time-dependent variation, and then we have all the source terms that can add, and this is the supply from the mechanical ventilation system, this is the supply from natural ventilation, this is the supply from infiltration, and this is indoor emissions, and then we have all the things that can lead to removal. The removal by air filtration, the removal by air exchange, or air change. Andy, are you still here? He's gone. I can say air exchange. And then deposition loss. The steady state solution is to set the left-hand term equal to 0 and then solve for C. It turns out that with some additional, so steady state doesn't often happen, but this is actually, this lowest equation is a decent approximation to the solution under time average conditions, subject to some qualifications, like you can't have A correlate too strongly with B. So I've argued and used this much more not to invoke steady state, but rather to say on a time average basis, if we're looking over a 24-hour period, this gives a good approximation of the underlying truth because the accumulation term will disappear on that time scale. Andy's told us enough about air change. Oh, look, air change rate. So I just have here some fits to empirical data, including actually some of Andy's for office buildings. The point that I wanted to make is that just that the parameter values here are in the range of about an order of magnitude from one building to another. That captures most of the distribution between about 0.2 and 2 air changes per hour, or per hour as the air change rate. Okay, if we introduce particle filters in the ventilation system, you heard a little bit about that from Andy. We can use that as a deliberate strategy with portable air cleaners. I'll talk about towards the end of our period. We can put better or worse filters in the mechanical ventilation system, and these will have consequences for the indoor exposure to particles of outdoor origin or maybe of indoor origin, depending on the configuration path. Filters that are employed for particle control mainly are of two types. Fibrous, in indoor environments, fibrous filters, which use the combined mechanism, actually the major mechanisms are inertial impaction and diffusion to the fibers. When particles strike the fibers, they stick, they're removed from the airstream, and the cleaner air can go through. The other prominent technique, which I don't have, it's not used as widely, and I don't have illustrated here, is an electrostatic precipitator, where a strong electric charge is placed on the particles through an ion generator of one sort or another, and then those particles are passed through a transverse electric field, and the electric field drives the particles to some collection plates, and they're removed from the airstream in that manner. Those are also used in indoor environments, just not as widely as the fibrous filters. The performance of a filter can be characterized individually in terms of what's called a single pass efficiency, and that's a measure for when you have air flowing through the filter. If you have a certain concentration upstream, what fraction gets removed as that concentration moves through the filter. So what gets through is 1 minus the efficiency. Efficiency of 1 is the best you can do, efficiency of 0 is useless. Because the smallest particles will diffuse to the fibers and the largest particles will impact efficiently, we end up with typically a U-shaped efficiency profile. And so for the plot that I'm reproducing here, which is from a textbook, the minimum efficiency, which is combining the effects of diffusion and impaction, settling, you can see, is unimportant compared to impaction. Interception I didn't talk about. We don't have to worry about the details. It's similar enough to impaction. But you can see the minimum combining all the effects is occurring at 0.2 micrometers, not very far from where we found the minimum elsewhere. And the overall performance is U-shaped. And the U-shaped behavior is actually very common. What differentiates good filters from bad filters in this space is how deep is the well, or how effective are the filters at the poorest, the most penetrating particle size. In fact, HEPA filter, high efficiency particle arrestants or high efficiency particle in air, kind of the gold standard, really great filter. The official certification of those filters is 99.97% efficient or better at 0.3 micrometers. So they pick the hardest size to remove, and they're almost perfect there. You see a lot of stuff marketed today that claims HEPA and probably fails to meet that very high-end standard. That high-end standard, by the way, was originally invented as a protection measure for nuclear power plants on the ventilation of nuclear containment vessels. And then it became commonly employed, inexpensive to manufacture, used in semiconductor manufacturing facilities, used for respiratory protection, for hazardous work, used for hospitals, used for semiconductor clean rooms. Did I say that? I'm getting a little punchy. Okay, so there is a U.S. standard. There's an analogous European one that uses a different front letter. So the U.S.-based measure is called MERV, And you can get MERV filters of various quality, and the lowest ones sort of, if you go below MERV 4, forget it, you got nothing. MERV 16 is getting into the neighborhood of a HEPA filter. And, but you can see in every case this U-shaped behavior, and that the minimum in the efficiency curve is kind of where you should expect it now based on what we've talked about already. I just have time for one little side note. I'll make it brief. I chaired a workshop in DC a couple of years ago, organized by the National Academy of Sciences, on the health effects of indoor particulate matter. And one of the sessions was about communicating knowledge in this space to the public. It was very interesting. You know, I learned a lot of stuff that I had no idea about. And one of the guys who was sort of an expert kind of scholar about communications of scholarly matters to the public, he looked at our stuff after the scientific presentations, including the discussion of MERV, and he was giving us a critique, and he said, you know, if I was in the public, I would say first, why is MERV 16 better than 1? We're number 1, we want to be 1. And then he said, who is this MERV guy anyway? Minimum efficiency reporting value. Okay, that doesn't really roll off the tongue. It's kind of like HEPA, what the heck? Okay, so also particle deposition indoors, U-shaped. Here's you know, somebody's summary data. This is actually from Brent Stevens' group, with minimum, 0.3 micrometers, and bigger particles deposit more rapidly because they settle fast, and smaller particles deposit more rapidly because the air will carry it by convective currents close to the wall, but the air can't carry it that last distance by advection. So that migration through the boundary layer adjacent to the wall has to happen through some other mechanism, and the very small particles diffuse faster than the somewhat larger particles. All right, I'll throw a wrinkle in here. Penetration, it's U-shaped, upside down, because we're looking at the fraction that get through, not the fraction that's removed. The physics is the same. Notice where the maximum is. Okay, it's, you know, as simple as possible, but not simpler. It's in the lower half of the accumulation mode. It's 0.1, 0.3, 0.5 micrometers. The details matter, but the general principle is consistent. And here's, again, from Stevens' group, Brent Stevens' group, some summary assessment of particle penetration as a function of, so the previous slide I showed you, that's a theoretical model calculation from my research group, and here's some assessment of what happens in real buildings. And you can see the general performance is consistent even if the details are different. So I wanted to say a little bit about sources, and so I just put up here a reference list, and you won't know this literature. That's what's getting emailed, the full references to all these. But I just wanted to illustrate for you the kinds of indoor sources for which we have studies of the emission characteristics. What mass is emitted, what's the particle size, how does it vary with the particular circumstances of that emission source. And so let's talk a little bit about how such experiments are done. The most common approach, either in the field, although those are really hard, generally really hard to do, or in simulated laboratory-based experiments in real chambers. So the real activity takes place in a chamber, but it's under controlled conditions. Let's say a room-sized chamber with controlled airflow, controlled ventilation, filter out all the outdoor particles. You know exactly what activity is taking place, you know when it's taking place, so you get the denominator and the controlling parameters right. And then you measure the particle concentration, and often these things are episodic, so the activity like incense burning or cigarette smoking or cooking is something that happens over a period of time. Generally don't get a steady state behavior. You have to deal with a time-dependent concentration profile. And the trick, to the extent that there's a trick here, is that one measures the concentrations with good resolution. Space is necessary, though you can often ensure that things are well mixed. Time, for sure. Maybe you can work with time average if you're clever. And size, definitely if you're able to do that. And then you infer what the emissions must have been to produce the concentration profile that you observed. So it's a little bit of an inverse problem mathematically, although we can solve it in a forward direction through clever application of the material balance model using what we can call the integral solution. So now we start with this material balance for, let's say, a controlled release activity in a mechanically ventilated indoor space, negligible infiltration, no natural ventilation. Filter out the particles from the supply air with a HEPA filter. We release the particles under controlled conditions in a time-varying manner, but that's an unknown. E is a function of time, the emissions profile. That's what we're trying to determine. We measure the concentration in a time-dependent pattern, and we have a few parameters. The flow rate we can measure, and then the deposition rate we have to characterize. We can do that in a separate experiment, perhaps. This is the starting equation. In order to get to the solution that we want, we're going to sacrifice the idea that we really want to know E is a function of time and say, we'll live with the sum over all time of the emissions. That is not the emission rate mass per time, but the emissions mass for that whole event, the time integral of E as a function, or times dt. So M, integrated over the entire episode of the experiment. Here's an example of an episode where we're measuring PM 2.5 concentration. The activity takes place, the concentration spikes, and then it sort of decays away. And what we're going to do is take a look at how the area under that curve informs us about what the emissions must have been, rather than the details of the time concentration profile. And we get to that then by rearranging this equation, integrating over time each of the terms, and recognizing that, well, this is the case in which we measured the end concentration and the starting concentration. So this is the mass that's released that's still in the room air, and this is the mass that's released that has been removed either by ventilation or by deposition. If we extend the analysis time long enough, we can make C at TE equal very nearly to C at TS, and then this part goes away, and this is just the area that's under the curve, and then these are parameters that we measure. So we can do an analysis then that gives us the emissions from that activity or event. There is a paper just published in Indoor Air in which this has been applied using PM 2.5 data from field measurements, actually, and they didn't even know what was going on inside the households, so all they have is an event happened, we see a spike, here's the mass of PM 2.5 that was emitted during that spike. It'd be nice if they knew more about what was going on, but it's useful even as a concept. All right, we're doing okay with time. Do we need to do jumping jacks? Or are you all right? No, it's okay. Let's take a minute and just stand up in place and breathe deeply or whatever. But really only 60 seconds. Get your blood circulating.
That also controls the temperature. Yeah, it's automatic. Yeah, I will detail you will come home, how will celebrate it? So, you go right around, what's your mood? Look at this one. This other dog. Because I'm still freelance student, I'm thinking when I find a dog, I will that culture.
Well, there are, but the difference. You want to get the reality.
To take like the majority of your time to take care of your child.
Okay, let's resume. I lost some people, but oh well. That was the risk. We're pacing well, so we will finish easily on time. We'll finish on time for sure, but we'll finish actually everything that I intended to tell you easily on time. Andrea presented this idea of infiltration factor, maybe using a little bit simpler conceptual representation of the factors that influence indoor particles, but the infiltration factor is aimed at answering the question, what's the indoor concentration of particles of outdoor origin? So we remove the possibility of indoor sources, and if we're thinking about this from a material balance and governing equations or influential factors point of view, we can use this same diagram just with the emissions removed from the story, and then ask the question in a sort of steady state material balance point of view, what's the relationship between C and C naught for the schematic. So we set up the same material balance that we set up before, and then we make an argument that either steady state would apply, or to a decent approximation, we can use the time average values of the input parameters and estimate the relationship between F and the infiltration factor, this indoor to outdoor concentration for particles of outdoor origin, as the relationship between, basically all of these are the source contributors, so the particles that flow in and are not filtered in the supply air, particles that leak in by natural ventilation, the particles that penetrate through leakage, and then this is the sum of all the removal mechanisms, the deposition, removal by recirculating filtration, and removal by any air change exhaust or air change flow out. In general, F is particle size dependent, and clearly from this expression, F is going to be a function of the operational parameters of the building. It matters whether you've got mechanical ventilation and how good your filters are and so forth. There is a nice review article published the early part of this decade in Atmospheric Environment that included this figure, which has a recapitulation. It was a literature review of all of the indoor-outdoor particle studies, but all of the infiltration factor studies as well. And what I want to highlight here, each one of these bars represents the central tendency of a determined infiltration factor for a particular study. The stuff to the left of the dashed line is for PM 2.5, and the stuff to the right of the dashed line is for PM 10. And a key point that I want to draw to your attention is that a pretty good central tendency for PM 2.5 from all this work is 0.5. The details matter, maybe the variabilities between 0.3 and 0.7. If you're aiming to understand central tendency, 50% isn't a bad guess. And that number is somewhat higher than you would find for PM10. Why? Because the coarse part of the PM10 doesn't penetrate and persist as well as the accumulation mode does. Earlier than this paper, this review paper, Riley, actually this is the same paper that I quoted from in the 3-paragraph introduction. So we published this paper in Environmental Science and Technology on understanding the size-dependent influence of particle behavior when trying to connect outdoor particle levels to what would occur indoors. And the ideas are still solid, although the data could certainly be updated now. But we didn't call it the infiltration factor, we call it the IPOP, but that didn't stick. It was the indoor proportion of outdoor particles. I like that better. Infiltration factor doesn't tell me what it is. But anyway, we lost, and like Andy, I can't get angry about every little thing that we lose. So we're calling it the infiltration factor now, just to be consistent. So here's a model prediction for residential urban air under typical ventilation conditions, and then with the central air continuously operating, but with a low quality furnace filter. And you can see our estimates for PM 2.5, 0.8 at the upper end, 0.5 at the lower end. we're in the ballpark of what empiricism would produce. And then if you were in an office environment and you had a MERV 8, which was then called a 40% filter on the dust spot test, or a MERV 12, which is now an 80, or then was an 85% filter, you might get somewhere in the range of 0.2 to 0.7, a little bit better, but again, centered reasonably around a half. You notice this isn't all that different from what I showed you from Singapore, when years later we went around with this portable air monitor and we found that buildings provide about 50% protection from our PM 2.5 exposure. So I then wanted to get to this point, and it really comes back to the beginning, when I told you that indoor particles matter even when we're talking about ambient particulate matter as a consequential health-harming agent. So this is something of a big-scale intake estimate, considering a U.S. population, assembling with fidelity to the underlying truth, but not worrying about the details. It's inspired by Einstein. The different elements. What is the mass of particles that get inhaled by the U.S. population in a year, considering only particles of outdoor origin, but allowing that people aren't just outdoors? All right, so here's the estimate. The total is the outdoor concentration. That should be an average population weighted over everybody. I'm going to really finesse that one. The breathing rate, how much air per year you inhale, that we know pretty well. Then the fraction of the time that we spend in our residences, we know that from survey data, times the fraction of the infiltration factor for residences, plus the time that we spend in other indoor spaces that aren't our residence, times that infiltration factor, plus the time that we spend, the fraction of our time we spend outdoors, times no infiltration factor, it should be 1. So here are the numbers that I used. Typical PM 2.5 for urban air in the United States. Most people live in urban environments, 10 micrograms per cubic meter. Volumetric breathing rate per person, we can discuss whether that's right or not, but it's pretty close, 5,000 cubic meters per year. Here are the values. I showed you where the fraction of time spent at home, at least in California, is 60% or so. And I took an average of the numbers from the Riley paper, 0.5 and 0.8. To get to 0.65. Here's the average of the office version of representing other indoor environments, fraction of time we spend indoors, not at home, and then the fraction of time spent outdoors or in transport microenvironments. Add it all up, and you get each person inhaling 32 milligrams of particles, of which 60% is particles of outdoor origin that they inhaled while they were indoors at home, and only 20% of which occurred outdoors. So 3 times as much of the particle mass that we're inhaling from outdoor air pollution is residential, and then there's another part that's comparable in scale from other indoor environments. And we added up for the whole 300 or so million people in the US, we end up with 10 tons per year of airborne particles in our collective lungs. Well, actually, that's not quite right. That's not the deposited part, so that's the intake, not the uptake. About half of that's going to be taken up, so it's 5 tons per year depositing in our lungs. And we got about 35% protection relative to the number that we would have gotten had we spent all our time outdoors. That's the aggregate protection of being indoors some of the time and the protection factors. That's pretty amazing, isn't it? That just like back of the envelope can produce some powerful numbers. All right, I think the last thing, it's only sort of 8 slides left. The last thing that I wanted to say a little bit about is air cleaning as a deliberate strategy for protecting people from exposure indoors, from exposure to particles of outdoor origin, or maybe from particles of indoor origin as well. And if we think sort of broadly here, we have 3 main approaches to improving indoor air quality. We control the source, so we don't smoke indoors as much as we used to. That's an example of source control. We do a better job with ventilation, make sure we don't seal our buildings up too tightly without providing for a good mechanical ventilation. And the third one is we clean the air if we need to. And we know how to do this reasonably well now for particles. We're not in a good place to do it widely for gases yet. So many factors can influence air cleaner performance. I want to focus with these remaining few minutes on just one aspect, which is the flow path and the configuration of the flow path. And I want to introduce an idea here of the contrast between an open path and a closed path. You call this pathway, right? Not route. Pathway of exposure connects the source to the receptor. So the open path and closed path ideas fit in with that. If the air and the particles from the source must pass through the treatment unit before getting to the receptor, then we have a closed path control intervention. If it's possible, based on the configuration, that the air can bypass the control unit and the particles can go by a pathway from source to receptor directly, then that's an open path. Now, it may seem like open path is automatically worse than closed path, but it's not true. It really depends. And so I've illustrated here, configuration-wise, a few ideas. So if we only have an outdoor source and we have a tight building, then we put a filter on the mechanical supply and we have a closed path control intervention. Here's an indoor source that has, you can imagine a 3D printer in a case. The 3D printer is emitting ultrafine particles. We put it in a sealed case and we exhaust air through a filter. That's a closed path control measure. Here's an open path opportunity where we put in a portable air cleaner that recirculates with a fan through a filter, but nothing guarantees that the receptor, not pictured here, is going to breathe air only that goes from E through that filter. So that's an open path configuration. We talked about the idea of efficiency as one of the metrics. What fraction of the particles that pass through this control device are removed? So that's going to be given the symbol eta. We also have, and this is sort of standard language now, even in commercial practice, something called the clean air delivery rate. So the clean air delivery rate for a portable air cleaning unit is the product of the single pass efficiency times the volumetric flow rate through it. So it's measured in cubic meters per hour, for example. And a CADR of a particular value, let's say 100 cubic meters per hour, is functionally equivalent when deployed in an open path configuration to having 100 cubic meters per hour of ventilation with particle-free air. Now, effectiveness, as I mentioned at the beginning, we'll use the symbol epsilon for. That's an indication of what's the consequence for our intervention in regards to the influenced concentration that we care about controlling for limiting exposure. So that would be indicated here by the concentration without control. Basically, you take this thing away. What's the concentration that you get from outdoor source or from indoor source or a combination? And then you add the control unit. What's the concentration you get? The difference between those two, normalized by the uncontrolled condition, is the measure of effectiveness. When effectiveness is 1, that's great. That means our controlled condition is 0, and the ratio 1 to 1, or uncontrolled to uncontrolled, is 1. And when the effectiveness is 0, it means that adding this control unit did nothing, that the controlled condition and the uncontrolled condition are the same. So it has the right kind of intuitive feel, and it's more closely linked to the exposure condition than the efficiency would be. Of course, these are coupled. So when you have a closed path configuration, some simple rules apply. Doesn't matter whether the source is indoors or outdoors, efficiency and effectiveness are the same. In order to get good performance, to get good effectiveness, you just make the efficiency as close to 1 as you can. For an indoor source, never mind, the CADR isn't important under those conditions. But another important detail is that the performance is the same whether you are interested in the time-dependent behavior or the response to a peak release or a response to time average challenge. That is, the concern is time-integrated exposure. You get the same outcome in this condition. So all of that generates easy math, easy analysis, and in fact, if that was the whole story, it wouldn't have even been worthwhile to differentiate between effectiveness and efficiency. They're the same. OpenPath, though, doesn't produce that result. We get a clean air delivery rate that's the product of the flow rate through the recirculating filter and its efficiency. The key qualitative features comparing effectiveness to efficiency in steady state, that is, or time average performance, you want to compare the removal by the thing that you've introduced to the removal by all other processes. And if the removal by the thing that you've introduced is high compared to the otherwise mechanisms or rates of removal, then you have an effective intervention. And if so just to put if the reverse is true, then you have an ineffective measure. So you can put a 100% filter, efficient filter, a HEPA filter, on a desk with a little fan, an instrument cooling fan from a computer, and it'll give you a CADR of 1 cubic meter per hour, 100% efficient, but the effectiveness will be negligible placed in any room size environment, because already the removal by ventilation, the removal by deposition is vastly larger. And that's the point in which it's necessary to think about why is effectiveness mattering when we're thinking about exposure and not just efficiency. You know the idea that green plants are really good for us, right? And we should clean our indoor air by just putting in a few green plants. That fails under the same argument that the clean air delivery rate of a green plant is pathetically small. There may be some benefit, but you need to have like greenhouse scale density of vegetation. Although I say that, and then Michael Waring's published a nice paper, his group, on this green wall that's in this building and how well it works. And there's some merit in that case because they're actively moving the air through that. But I digress. An important detail also is that if you're concerned about transient peaks, the performance is not the same as in a time average value when you have an open path flow system. You can set up the material balance, you can do the analysis to demonstrate that that's true. So I just show you here this quantitative representation of what the what the performance looks like of a portable air cleaner measured in terms of effectiveness on the steady state or time average scale when you're comparing the CADR to the removal by other mechanisms, ventilation plus deposition. And you need to have at least 1 to get up to 0.5, and if you're going to have a really good performing unit, you better have 10 as the CADR compared to your other rates of removal. And if you've got 0.1, don't bother. You wasted your time and money. So a few closing remarks. There's some really interesting and important research frontiers in the indoor PM world, and so this is a list of some of the topics. I won't bother reading them off, but I did send you, or we will be sending you shortly, this reference list, which would be a good place to kind of gain access to the literature in these various subjects. And I just wanted to close with, okay, so you never apologize, as Trump's teaching me how to never apologize. I'm always, willing to admit my mistakes, and this isn't exactly a mistake, but it's sort of a mea culpa that the first tutorial that I gave, the one on writing earlier today, or the first lecture, was one that I had prepared for the Ghent meeting, and then I just needed to update it. We did Indoor Air Summer School 1 2 years ago in Belgium, and this is number 2. And so when Mike and Brent and it was nice that they gave me credit in that group of 3, but they did 98% of the work, and I talked to them a few times. When we talked about the summer school and the organization of the summer school, they said, why don't me, I do exposure and the writing one, that was a good one. I said, and we'll have Andrea do particles. And I said, I would rather do particles because Andrea really actually did most of the work on that exposure tutorial before. And then we agreed on that, and then and she agreed, and then I realized that I actually didn't have anything prepared. I had my particle lecture, I gave particle tutorials in the aerosol conference years ago, and it was so out of date that it was almost useless. So I had this, not exactly a panic, but realization that I needed to put in some days to put these slides together for this talk. This one I ran out of energy to say something brilliant, so that's my mea culpa. But anyway, I wanted to share just like a broader perspective about the space that we're concerned about as indoor air scientists. And that's just an issue, a couple of dimensions of scale. So the Earth's atmosphere is finite. You can measure it, you can actually determine it by force balance, the pressure at the surface of the Earth multiplied by the surface area of the Earth equals the mass of the atmosphere times the acceleration of gravity. And based on that, which is accurate to a few tenths of a percent, maybe to a percent, when you account for the mountains, you actually can do better. It's 5,000 exagrams. Okay, exa is one of those prefixes that we don't get to use very often. It's 10 to the 18th, but it's finite. It's 5,000 exagrams. We collectively, the 7.5 billion of us on the planet, breathe 10 parts per million of that atmosphere every year. Well, that's kind of stunning, right? I mean, you can think that's small, but you can also think, whoa, that's not such a small number. We use about the same amount of air as combustion air when we burn fossil fuels, like in coal-fired power plants and in our cars. We ventilate our buildings with about 100 times the rate at which we breathe air, or 0.1% of the entire atmosphere passes through our buildings every year. And cities, if you think about, Hugo Lee, the new editor of Indoor Air, likes to think about Hong Kong as just this giant indoor environment. The city of Hong Kong is indoors because the ventilation of that city is like, it's naturally ventilated, complex building space with these a few openings between all the buildings, and they have to count on the wind and the temperature difference to drive the airflow. And he starts to think about, the city of Hong Kong in analogy at larger scale with our environments. So cities are ventilated in effect by nature with about 1/10 of the full atmosphere. That is, 1/10 of all the atmosphere will pass through one city or another during the course of a year. So, we're thinking about particles in indoor environments, and the scale of the particles varies vastly from the coarse particle blue whale to the nanoparticle shrew. But then when we put the particles onto kind of the length scale of the world that we care about, just limiting ourselves to the terrestrial space, we have about 16 or 17 orders of magnitude between the atom and the diameter of the Earth. And the particle space is sort of real there, but when viewed in this log scale, it's kind of like the relationship between an ultrafine particle and PM10 isn't that different than that between a human and the city. And so we need to think, I keep coming back to Einstein, my kind of anchor point for a way to cleverly think about the world. It's hopelessly complex, but it's not overwhelmingly so. And we need to be clever and strategic and wise in how we utilize our resources and not get lost in all the details, except in the cases where the details matter. But the goal is to get general understanding and general truth out of particulars. And it actually doesn't matter whether it's particles that you're studying or some other aspect of the indoor environment. We're 7 billion people, a comparable number of indoor spaces, 10 to the 5th pollutants, 3 billion seconds per lifetime. And, we're going to get lost in all the details. But the ideal gas law works, even though there's 10 to the 22nd molecules in, a few liters. And so there are some general things that we can extract out of this. Anyway, I'm beginning to ramble. So I don't want to keep us any longer from dinner. Thanks so much for your attention. I'm glad to still see you all here and awake. And again, I left no time, but we can discuss over beer and whatever else.
Thank you.